Attendees are welcome. Welcome, Mr. Pascal. I am Bara Mahmoud, a student in Engineering Technical College, Department of Fuel and Energy Engineering. I will be the moderator of this session today. Our session, named by
Okay, thank you very much. Um, Welcome, everybody. I guess everybody here is a chemical engineer, correct? Did you hear my question? I
Before
said,
we
is
start,
everyone?
sorry, sir. Before we start, I'd like to note the mics and cameras are closed by everyone, and any question you can write in the chat box will be answered by the professor of the session of the end of this our session. If you have any participation, you can discuss with Mr. Pascal at the end of this lecture. There is also attendance certificate and a registration link will be sent at the end of this lecture. Thank you, everyone. You can start, Professor.
All right. Am I allowed to use my screen, my camera, or is it okay like this? Is it fine like this, or can
Yes,
I on
yes,
my
it's
camera?
allowed to you.
Okay. Let me see if that's gonna work. Okay. All right. So, good evening, everyone. It's a pleasure to be with you all, and thank you for inviting me. I actually just came out of work and rushed here to make this presentation, and I'll do my best to make sure everybody understands. Okay. Because I like the fact that everybody here is a chemical engineer, and I asked and I heard that you guys have a little bit level of FCC. So my job here is to give a slightly more detailed version of the FCC. Okay, that's fluid catalytic cracking, so that who knows, if you work in a refinery tomorrow, you simply have an edge over every other person. Okay, so with that, I would start my presentation. And before I start, assalamu alaikum to everybody. Okay, all right. Please, in case there's any issue, please stop me because my screen is full. Uh, the moderator should stop me in case there's any break in transmission or any issue about audio or video. All right. And with that, let's start the presentation. Any questions so far? Okay. All right. So let's go into the main course for the day. Fluid catalytic cracking, an overview. My name is Pascal Ndonago, and I'll be your instructor for today. So this is the outline that we're going to work on today. We'll start with a brief history of FCC, then the role in the modern refinery. Then we'll talk about the FCC feed, based on classification, properties, and impurities. Before going to the chemistry, which is basically reactions. After that, we'll talk about the process description, which is going to take a lot of time because that's the meat of the topic. Then we'll talk about the catalyst, which is the lifeblood of the unit, the product, and the last request, which I was told optimization options. So a brief history. Um, the start of the FCC refining industry has its roots in the rapidly growing demand for fuels. So way back in the 1800s, um, what people wanted was kerosene to light up their lamps, right? But with the invention of the electric bulb and cars, the choice of fuel moved from kerosene to gasoline. Okay, and the demand also got so high, especially during World War II. Okay, and we got to a point where the available naphtha or gasoline, which could be gotten from street run CDU was not able to satisfy everyone. And at that point, the bottom of the barrel, which is the last product of the atmospheric distillation, was just thrown away. And somebody had a great idea. Why don't we further crack the atmospheric residue and squeeze out some gasoline from it? And thus the FCC was born. But before the FCC was born, there were some previous technologies that gave birth to the FCC. And because the FCC is a form of cracking, in this case, catalytic cracking, there was a, if I may say, older brother of the FCC, which was the thermal cracking. Now, thermal cracking simply used high pressure and temperature to get out as much distillates as possible, your naphthas and your gas oils. Okay, but the yields were not so palatable, and they generated a lot of gas, which people didn't like. So we went on to start using catalysts in the 1930s and 1940s by the Hondro process. It was a breakthrough in the sense that we could lower the activation energy of the reaction. We didn't need much heat or pressure, right? But it was slow because it was more like a batch process. Then we got to the moving bed catalytic cracking, which was another step. There were advances in catalyst, okay? But the final product was the fluidized catalytic crack, which is a continuous process. It can run all year round. And our catalyst became finer. The studies of catalysts became very, very significant during this period. And we all know that bigger surface area is good for chemical reactions. And this is what drove the FCC into one of the most profitable units for fuel processes in the refinery. Now, one of the questions you might ask is the role of the FCC in the refinery. If you look at this graph carefully, you would see that for a typical refinery, for a high conversion refinery, because there are different types of refineries, but for a high conversion refinery, you will see you have your gas, which is recovered, which you can be able to recover your LPGs from, liquefied petroleum gas, for your cooking. You have your naphthas, which would still be split into the heavy and light naphtha. The light naphtha goes to isomerate, and the heavy naphtha goes to the reformate. All the places that I put the red star, okay, are sources of potential gasoline products for blending. Because gasoline is not just one product. Gasoline in a refinery is a collection of different gasoline range fuels. They can come from butane, which helps in the RVP. It can come from naphtha, which is the precursor to isomerates and reformates. It can come from alkylates, which is the best form of gasoline, in my opinion. It can come from FCC, which produces the bulk of gasoline in the refinery. And you can add ethers and ethanol. Now, we consider the FCC to be the mother, to be the heart of the refinery. Because if the FCC is down, the tendency that hello? 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 I heard a noise. Should I continue? Moderator? Okay. All right. All right. Okay. 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 All right. So, where was I? So the FCC is considered the heart of the refinery because, as I said, if the FCC is down and you're in the refinery, the manager will be panicking till it gets back up because it produces the bulk of the gasoline. Now, to see how important the FCC is, if you look at this chart over here, these are different blending gasoline products, which at the end of the day is blended together to form gasoline. You can see in China and the United States, FCC is the highest volume of gasoline in your product in the gasoline pool. In Europe, the highest is reformate because Europe has a very, very stringent environmental constraints, which makes the FCC not really the best option for producing gasoline. Right, but in the United States and China, you can see compared to other products like butane, naphtha, isomerates, alkylates, it is obviously higher. Now, FCC is also important because it is the products. Without an FCC, you cannot have your alkylation units and units like polymerization. So it's also very important for the production of these alkylates here. Okay. All right, now, so we'll go into a very brief description before we go into details. From a block flow diagram, and I'm sure you guys are students, so you know what block flow diagram is. I'm glad. From a block flow diagram, you can break into 5 different segments. When the raw oil comes in, you have your catalytic section, which is mostly made of your reactor and regenerator. You have your main column, which its main job is to desuperheat the vapor products, where you can be able to draw out other major products. Then from the overhead of the main column, you have your wet gas concentration unit, where you pull out your gasoline and your LPGs and your fuel gas. From the regenerator section, you can have your power section if you want, and you have your fuel gas cooler section to extract as much energy as you can to produce steam. This is a process flow diagram of what I've said here. Your regenerator, your reactor, main column, and gas concentration. Now, it's very important for us to observe something. When you go to a refinery and they tell you this is the FCC, there are some things you should know. You should know where the regenerator is, where the reactor is, and where the main column is. Chances is that they are all together. But what's the difference? The regenerator will always have a bigger diameter. Okay, it's usually shorter and will have a bigger diameter. The reactor will be taller and slimmer, while the main column is always beside the reactor, and it looks like a main column, a normal column. Okay, and to buttress this point, I'd want us to do a little exercise. Okay, I would want just one person. If I point at a particular image, I want someone to say whether it's a reactor, a regenerator, or a main column, based on what I just said. So this will be a quick exercise. Just anybody can just, say something. Okay. So, what is coming? Okay. So what is this? Someone can just open your mic and say what it is. Is it a regenerator? So by RX, I mean reactor, RG, regenerator, MC, main column. So what is this? Can somebody just open his mic? Anyone? Okay. All right. I'm just seeing this. Someone is raising his hand. Okay, unmute yourself, please, and tell me the answer. Mohammed. Anybody? What's this? Don't be shy. Just give an answer.
Sir, could be top left is the regenerator, and in the middle could be the Rx, which is the reactor, and to the right, the main column, maybe.
All right. Okay. All right. Thank you, Ali. Okay, so now to this picture. This is a little bit confusing, but you should get it. It's gonna be good. So, what is this? Somebody else?
Can I go again?
Okay, if everybody's
Yeah.
keeping quiet.
Could be that. Okay. In the middle could be the main reactor.
Okay.
This is the
So
main
what's this?
column, and to the right is the regenerator.
All right, beautiful. So the regenerator is always chubby looking, okay? Right, the reactor is slender and tall.
Could be that. Okay. In the middle.
All right, beautiful. Okay, so with that, let's move on. Okay, so we are going to talk about the FCC feed and characterization. Now, FCC is a very unique process because it takes in a very, very wide range of feed. Okay, I don't know how detailed you guys are with your refinery block flow diagrams, but it takes in the vacuum gas oil, which is the primary feed. This is gas oil is getting from the vacuum distillation column. The new FCCs, which are called ROFCCs, residue fluidized catalytic cracking, taking the atmospheric residue. So there is no need for a vacuum distillation tower, saving capex. It also takes in DAO. Now, DAO is the asphalted oil, which is a product of SDA, solvent deasphalted units, the asphalting units. Okay. You can also take in hydrotreated gas oil, which is a gas oil that just came out of the hydrotreated vacuum hydrotreater, the hydrotreated vacuum gas oil unit. You can also take in the cracked gas oil, a product of your thermal cracking unit for columns for refineries that have coker units, and refinery slop, which is a mixture of oils that most refineries produce as waste. And you have biofuels. Biofuels is a new study. Most research ongoing in FCC, are talking about how to convert, your oils, your vegetable oils, your waste oils into gasoline by using FCC. Okay. And now this is a sample of a VGO from Kabbalah Refinery, the new MRC Kabbalah Refinery. While I was there, this is how the VGO, the light VGO looks like. Okay, this is how it looks like. This is how the heavy vacuum gas oil looks like, and this is when you blend both of them together. So this is fed. You can feed any of this, but when you blend it together, it comes up with the right texture and density and the rest, and you process it. So this is basically your feed for this. Now, we're going to go into classifications. If you can remember your PONA analysis, which is your paraffin, olefin, naphthenes, and aromatics, that is also a classification for crude oil. Okay? Although in crude oil, we don't have olefinic crude oil because olefins is produced by a chemical process. So we have paraffins, naphthenes, and aromatic crude oil. And by that, the feed for the FCC would also take that that structure. Now, paraffinic crudes are crudes that have a lot of straight chains. Naphthenic crudes are crudes that have a lot of cyclic chains, and aromatics are the ones that have benzenes in them, benzene-based crudes. And the best kind of feed for the FCC are paraffinic feeds. You can see that the crackability is high. This is UOPK factor, which helps to determine what type of crude oil or oils you're dealing with. And the more it leaves the paraffin unit, the more difficult it is to crack. So it means if you crack a paraffinic crude or a feed, you're more likely to have a higher conversion than when you crack a naphthenic or aromatic crude. Okay? Then we'll also talk about impurities. There's some every crude oil has some form of impurities, some less, some sweet, some sour, but that also goes down to the potential feed of the FCC. Now, if we have sulfur in the feed and it's not dealt with, it can contaminate the product and the flue gas. The products, like having sulfur in your crude, in your gasoline, is not going to be a good thing. Having it in your flue gas, if it gets to the atmosphere, it might pollute the atmosphere. Also, nitrogen is another problem that we may have as an impurity. It causes corrosion and fouling, and because the catalyst, which we're going to talk about, it has a metal and acid sites. It can neutralize these sites and makes them ineffective for cracking reactions. Oxygen can cause fouling, and form water, which precipitates the corrosion. Now, your Conradson carbon. This is a very important parameter because this value helps us to know it's what people say the coke forming tendency of the FCC on your catalyst. If this is too low, it's a problem. If it is too high, it is also a problem. If it is too high, then you have to deal with excess heat in the regenerator, which we'll talk about as we go on. And if it's too low, the regenerator might not be able to work properly, as we will still talk about going on. Then, of course, metals. Metals are always a problem for catalytic processes. They cause irreversible damage to the catalyst, and the most notorious of them is nickel and vanadium. Okay. Now we'll talk briefly about the chemistry of the FCC. The FCC, the cracking process is an endothermic reaction. And by that, it means it simply requires heat to be able to work properly. Hence the need for a regenerator, where we not only regenerate our catalyst, but provides 90% of the heat for the unit. Okay? Now, long chain paraffins are converted to branched paraffins. Branching is important because the more we branch, the more we have, we can meet our octane numbers. Straight paraffins are converted to aromatics and paraffins. Ring compounds are converted to alkylate aromatics. Dehydrogenation of naphthenes to aromatics and hydrogen. And coke formation due to excess cracking or thermal degradation. So in this diagram, you can see the feed breaking up to the various product components. And we'll deal with this subsequently in the presentation. So you have your heavy oils. Primary cracking takes you to the gas and gasoline and LCO. Dehydrogenation reaction takes you to coke and residue. And this is the major product you're looking for, gasoline. Now, if you look at this diagram here, you can see a tiny ZSM5. This is an additive, which helps in producing polypropylene. We'll talk about it also as we go down. Okay, so at this point, do we have any questions so far? I would like maybe one question or two before we move to the main presentation.
Yeah, I have a certain question here, please.
All right.
About the K factor, how we can obtain it, and what is the parameters of the K factor?
Yeah, so the K factor is a parameter that is used to so if you have a crude oil, right, it's a function of temperature and a couple of other parameters, physical parameters, I think temperature, density, and some other parameter. It's okay, probably before the end of this presentation, I'll bring out the original formula. But it's mostly a function of temperature, I think density. It just helps us to, the parameter helps us to, in a very, very vague way, to tell us what kind of molecules are in the crude oil. In a very vague way. That's why you see that it is in the ranges. If it's greater than 12, it's paraffinic. It shows us that, okay, we have a lot of branch chains here. If it's within a particular range, it tells us, okay, it's naphthenic cruise. So it's a very, very vague parameter, but it helps to tell us how it behaves. But I'll get the proper formula probably before the end of this presentation. Okay. So I think, like, for where I come from, our crude oil is mostly paraffinic, right? I don't know, Iraq crude should be naphthenic or paraffinic. I don't know. But before the end of this class, I'll get some of this information for you. Okay? Ali?
Yeah.
Hello? Okay.
Yeah.
All right.
Yeah, it's clear. Thank you.
Okay. Any other question? Ali is not the only student here, right? I want one more question before we proceed. And if you're good, you can just do a thumbs up and we can move on. Can we move on?
I think it's good, sir.
All right. Okay, so in the outline of our presentation, remember I said the FCC is divided into the reactor regenerator, the main column, wet gas compressor, the power generation section, and the free gas section. So the reactor regen section is the heart of the FCC. So remember I told you that the FCC unit is the heart of the refinery. Now the reactor regen section is the heart of the FCC. Okay, this is where the magic happens. So heavy feed is cracked in this process and products are generated, from dry gas to your slurry oils. Now, the bulk of the reaction happens in the riser. The riser is a long tube, and it takes just barely 2 seconds for the entire reaction to happen, for cracking from gas to gasoline to LCO, for everything. It just takes 2 seconds. If it's more than 2 seconds, then you would have probably a lot of gas and coke. If it's less than 2 seconds, you might have maybe low conversion of the product. And the cracking is in vapor phase. Now you might ask yourself, how can something so thick, as I showed in the picture of the bottle, be vaporized? Yes, there are equipment that will turn the thick product to vapor. And don't forget that it is going to be heated up to reduce the viscosity. So the feed is going to be vaporized with steam, and the catalyst comes in contact with it. And once the catalyst comes in contact with it, it cracks and the reaction continues. Okay, it goes to the regenerator and sends it back. Now, but before we proceed, nowadays we might only be familiar with this type of FCC, but it was not always like this. The earlier models of FCC was what we had a stacked configuration, where the regenerator was down and the reactor was up. So they were stacked on themselves. And the feed would come in here. This is basically the riser. Before coming to the reactor, the product will leave. Okay. Now, when this happens, the coke is carbon. It gets attached on the catalyst. Okay. And it will eventually be burnt off in the regenerator via the stripper. And we all know that the product of combustion is CO2 and water. If it's incomplete combustion, we have CO. Now, these earlier models were smaller. You'd have a lot of partial combustion in the regeneration section. But the side-by-side model, which we're going to talk about a lot, can accommodate bigger volumes. Most of the ones you see, the new refineries, or from the 70s or from the 80s downwards, are all side by side. Okay, right. So let's move on. Now I'm going to talk about some basic concepts of FCC. Now, FCC has a lot of the side-by-side model has a lot of variations, a lot of models. Like your iPhones, you have iPhone 11, 12, 16. I've lost count. I don't know if they're 19 or 18 right now. So it's the same way with FCC. Okay, there are different models. So I decided to present to us the bubbling bed regeneration model. Okay. So now this is how it works. The feed comes in here. Okay. And at the bottom of here, it is atomized. I told you that the feed is going to be in form of it has to be a vapor form, so it's atomized, and it comes in contact with hot catalyst coming from the regenerator. Now they mix up, and within this long pipe or long conduit is the riser, and from here to here, the catalyst will take only 2 seconds, and this is where the whole reaction happens within this line. Okay, kind of like a plug flow reactor. Now, when it comes down here, when it gets here, the feed has attached itself to the catalyst, gotten cracked, produced products which are mostly in vapor. Now, when it comes here, the catalyst, because though it's in powder, it is light, but it's also a solid. So when it gets here, it falls down to this point here and stays here and comes down through this stripper. Now, at this point, the vapor product disengages with the catalyst, most of the catalyst, okay, and comes into this cyclone. I'll show you these pictures in the next slide. Comes into this cyclone where it spins, okay. When it spins, the essence of spinning is to be able to, okay, like imagine you have a pool of water with sand inside. When you stir the water, you will see that the sand particles at the bottom of the water tends to coagulate together while the clean water stays on top. That's what basically happens. So the cyclone spins a mixture of fine catalyst and product. The catalyst that refuse to come down here will join the vapors here, spin, and still drop down through the deep legs. Any remaining fine catalyst and product still goes into the next cyclone, spins, and drops down here. At the end of the day, there's a 99.9 separation in this cyclone, in these cyclones in the reactor. Now, this is if there's no damage to the cyclones, obviously. And the product lives here as pure vapor at the top to the main column. Okay? Now, at this point, you have your catalyst building up. And because there's no perfect reaction, you will still have some uncracked hydrocarbons attached to the catalyst. Then you have your steam, stripping steam. The essence of your stripping steam is to take out these hydrocarbons out of this catalyst, okay, through the cyclones back to this surface. Now, don't bother about the water. The water that will condense from the steam is going to come out somewhere else. Then with that, you have a relatively clean a catalyst with less hydrocarbons, but with coke. You cannot use steam to remove coke from the catalyst. The coke is still going to be there. Imagine coke to be like charcoal on the catalyst, okay? Now we go through this spent catalyst valve into this regenerator. Now, this regenerator, it has one major function, and that is to burn off the coke on the catalyst. Now, these catalysts are tiny particles. They have coke on it. It comes into here, right? It falls down through here, through fluidization, of course. And hot air comes in here and burns the coke. Remember that there's something they call auto-ignition. So coke has an auto-ignition of 650 degrees or thereabouts. Auto-ignition simply means it's a temperature where any material will combust without the need for an ignition. Because you remember your triangle of fire, you have your oxygen, you have your fuel source, and you have your source of ignition. But with auto-ignition, you don't need a source of ignition. It just burns at the right temperature. It just burns. So this regenerator has to be at a particular temperature so that coke will burn naturally, and that's what happens here. The air keeps coming, hot air, keeps coming and burns the coke. Now, just as we had here, okay, we have cyclones where instead of us to have our products here, we have flue gas. Flue gas is a product of combustion. So you have your CO2, carbon dioxide, carbon monoxide, SO2s, NOxes, and water, but in vapor form. Now you need to separate that catalyst from the flue gas. So the same function this that happens here is the same function that happens here. You keep spinning the catalyst inside, the catalyst drops, and the flue gas leaves the top. Now, for the energy balance of this unit, we have heat energy from different sources. We have the feed in. The feed would pass through preheat exchangers, heat exchangers that will heat it up. You have your recycle, your feed recycle from your main column. I'll show you that. You have your air. Your air is going to be heated up, as I told you, and you have your steam. Therefore, where we lose air, you have your reactor vapors, which is called effluent. You have your flue gas, which leaves from here, and you have miscellaneous losses, like heat loss to the environment. And in all, and heat of combustion is generated inside. Heat of cracking absorbs the heat of mostly of this combustion. Okay, you have heat of vaporization where we atomize, and we have a cat cooler losses, which I will explain in optimization part of this presentation. I know that's a lot, but I'm still going to ask you for questions. Now, the fluidized catalytic cracking will not be complete if the concept of fluidization is not applied. Remember, as I said, the catalyst is it's like powder. In fact, it's finer than powder. Okay, you know how a powder looks like. It's finer than talc powder. And for us to understand the concepts of fluidization, when you put the FCC catalyst in a tank, it behaves like a solid because, it takes up space and it's fixed. Now, by the time you start putting low velocity through it, low air through it, it still looks like a fixed bed. Nothing is moving. If you increase the velocity of the air or the lift medium or the gas, the bed begins to increase. It begins to develop what they call a head. It begins to start behaving like water. Okay? If you increase the velocity again, the air will start bubbling through this catalyst, which is a solid. If you increase it further, you have slugging, and if it's high velocity, it now turns to it's just a form of transportation, pneumatic transportation. Okay? Now, if you look at this is fixed bed, we keep increasing the velocity. It's relatively stable, but at a particular velocity, we have head loss. It behaves like fluid. Now, to bring that to this reactor region, at this point here is the riser. All we need in this riser is to take the feed and the catalyst all the way through the riser down to the top of the reactor. So there's a lot. We have a lift gas, which makes here to behave like this. Okay, and when all this is happening, the catalyst is moving. Okay. So, and the best way to represent this is density. You can see we have a very low density here. This is just 80 kilograms per meter cube, very low. This is 30. This is where you have your fines. In the stripper section, you have mostly the bubbling stage, because remember that your stripping steam is, pushing the catalyst through, and it comes down, bubbles down, and comes down here, still bubbling. The air keeps helping the catalyst to move. Okay, it keeps helping, and that is how catalyst moves throughout the whole reactor. Okay, I expect questions from this. Now, your main column. In the previous slide, I told you that all our products that comes out of here is vapor. Now, the main column's job is basically to desuperheat the vapors. Now, in your chemical engineering, I know you must have designed columns, okay? McCabe and Thiel method and the likes, using your simulations. Whenever a feed comes in at the top of the column, it's most likely the feed is in liquid, correct? Yes. When it comes in the middle, it's most likely a two-phase liquid and vapor, a feed that has liquid and vapor. But when the feed comes at the bottom, it is gas. And when it is a gas, we try to turn it back to a liquid by, making it come in contact with liquids that will remove the heat from it. That is why in the main column, you see a lot of pump arounds. This is a reflux. This is a pump around. This is another pump around. This is another pump around, HCO pump around, and this is another pump around. Altogether, I have like four pump arounds. Okay. And the whole essence is to take out the heat from this vapor in order to be able to recover products along the column. Okay. So you can have your heavy naphtha fractions, your LCO, your HCO, your slurry oil. Okay. You recover all this because you are able to desuperheat. Now, for the vapors that leave the top, the vapor is in the vapor that leaves the top of this main column. That is where you have your gasolines and your LPGs. Now, I know it's kind of like difficult to understand because you'll be wondering about gasoline is liquid and, but yes, the temperature is so hot that your gasoline that you put in your car, your premium motor spirit, is still going to be vapor. Okay. Now you now have the wet gas concentration units. It's called wet gas because you find your LPGs and your gasolines in this process. The overhead of the main column comes into the compressor, compresses it, you have your interstage coolers, and takes it to the high pressure receiver. This high pressure receiver is also considered the heart of the main column of the wet gas compressor. If anything is wrong with this vessel, oh, okay, I need to show my pointer. Sorry, let me give my pointer. Okay, all right. So if anything wrong happens to the HPS, the whole system goes down. It's the pressure. Is the unit before the high pressure and the low pressure side of the wet gas compressor. Now the vapor part of this high pressure separator goes to your primary gas absorber, where LPGs will be recovered from. Okay, you use in the case as the name implies, high primary absorber. You use some form of oil, or your stabilized naphtha to recover LPGs. Okay, and the light gas from this goes to the sponge absorber, where there's a final polishing, picking off any LPG. So remember that LPGs is C3, C4. Okay, so that what is left in your off gas is C2s and the lights. That's what happens here. The liquid from the HPS, high pressure separator, goes to the stripper, where the temperature is controlled in such a way that the light ends are taken out and taken back to the feed to the HPS. Okay, now this product is where you'll finally get your LPG, C3, C4, and in some cases, your gasoline. If you don't have this, you can simply have your gasolines from here. Okay, it's at this point that you control all the compositions. So the operators are very, very important in this point. They control This is where they now control, your RVPs, your distillation cut points, and so many other parameters to make sure that your products come out as per regulation and as per what the customer wants. Okay, so now the last part of the FCC unit before question time is the flue gas session. So I've put in 3 different schemes that different refineries use. Okay, so from your regenerator, I told you have your flue gas, and your flue gas will also have fine catalyst. This fine catalyst is okay. Your flue gas is hot, and we're looking at temperatures of 680, 700 degrees centigrade. And we're looking at pressures of maybe 2 bars and the rest. Not high pressure, but high temperature. So the problem is, how are we going to reduce the pressure to atmospheric pressure? Because we cannot release the atmosphere directly. And how are we going to recover the heat so that we don't cause heat pollution to the environment? We're also bothered about removing the catalyst fines, which will follow it here, and environmental emission control. When the fines and the flue gas leave here, this is what they call a double dick slide valve. Its job is to reduce the pressure by 1/3. Okay? Then they go to the third stage separator, which is like a modified cyclone. We have catalyst fines that will be recovered from there. We also have a orifice chamber, which further drops the pressure. Then we can now use the heat for other productive things, then generate steam. We also have an ESP, which is the electrostatic precipitator, basically for environmental emission controls. It's the last place where you take out the smallest fines so that it doesn't get exposed to the atmosphere. In this case, we have a third stage separator, double disc slide valve, an orifice chamber, and a boiler. In this case, we have a third stage separator, a boiler, but we are able to use the high pressure to generate energy by having an expander. Expander is the opposite of a turbine. Okay. And with that, we can use to power, maybe provide electricity for the refinery or power other engines in the refinery. Okay. Now, it's important that despite the fact that there are different schemes, it also has different costs. If you're only dealing with a 2-stage cyclone, which is what is in the regenerator already, which I told you takes 99.9% of the fines, that's okay. If you're going for a 3rd stage and 4th stage separator, you have higher efficiency in removing the fines, but the cost keeps going up. You can add a wet gas scrubber, electrostatic precipitator, and the more options you have, the higher the cost, but the higher the environmental compliance. Okay. I'm going to play this video. I'm going to play this video now, and please let me know if you hear what is being said. Okay. This is going to summarize all the things I've talked about for the past maybe 30 minutes. Okay. Let me know if you hear it.
Yes, sir, it's in.
Can you hear it? Hello?
Yes, sir.
You can hear the video, right?
No, there is no voice.
There's no voice.
Try again.
I was worried about that. Okay, I'll try again. Let me see. This. Can you hear it? Did you hear it? No.
Sorry, sir, there is no voice. I can't hear anything.
Okay, let me try something. I'm just not gonna waste my time. Wait, let me try something. Still no audio.
Sir,
Do we have any
can
IT
you
group?
check the setting of share?
Yep.
Check,
Yeah.
check the setting of your share screen. I think you need to do a full for a share for a full screen. Check your setting, please. Yes, I think this is good.
Okay. Okay. Let me. Okay. So let me check. Let me check the setting. Video. Audio.
The
Sorry,
audio
guys.
setting. No problem. Take your time. The audio setting.
Yeah, I'm trying to. If there's an IT, if there's an IT expert, you get if the tech. Let's see if it works now. Still no voice. Let's, just give me a sec. So, in Google Meets. Okay, if you tab. Okay, okay. Yeah, just give me a sec. Not so sure. Um, okay. Um, okay. Sorry, guys. Just trying to get this working.
So if it doesn't work,
Yeah.
you can send to us the link, and we.
Sorry, what do you say? Hello.
I suggest to send this link to us, and we will send it to send it to the attendance later with the certificate.
Yeah, okay. Okay. I think I'll do that. Let me just try one more thing because it's actually a summary of everything I've done.
Okay.
Let me just check on that. Oh, okay. I think I've seen the problem. Let me take off my headsets. Let's try one more time. Is it working? Is it working?
No.
No. Okay. I mean, okay. All right. Let's Okay. Let's go ahead. Yeah. Sorry about that. Oh wow, that's bad. Okay. All right. Since it's not working, I'll try and get it running before the end of the class. Okay. Is that okay?
Yes, yes. Okay, no problem.
All right. Sorry about that. Oh man, should have. Okay. All right. Okay. We're gonna do something. I'm gonna allow it to play. Okay. And while it plays, you can hear me, right? You can hear me well.
Yes, yes, I can hear you.
Okay. So while it plays, I would explain what's going on. Okay. That's what I'm gonna do now. Stop sharing. Let me just reshare my slide. Okay. And sorry about that. I don't like when everything doesn't go according to plan. Okay. All right. So I'll try my best to explain what's going on. Okay. It's not going to be 7 minutes. Maybe after 4 minutes, we'll move to the next slide. All right. Okay. So at this point, you can see the catalyst coming into the riser. Okay. This is the atomized feed, okay, and you can see it coming in contact with the riser with the catalyst. Hot cat. Wow. Now this is the top of the reactor where the vapor now goes to the main column. Falls down. Means that to the cyclones. Okay, see what's going to happen. Okay, I'll play this video at the end of the program. Is that okay? Is that fine?
Yes. Yes,
Okay.
it's fine.
Yeah, I'll play it at the end. Please, if we have any IT guru amongst you, please help us get the answer to this, the solution to this problem. Okay, I believe there's an IT person amongst you. There's always one person. Okay. All right. So let's go to the next slide. We're going to talk about the FCC catalyst and additives. So, but what is the FCC catalyst made of? It's made out of a couple of major ingredients. First of all, is zeolite. Zeolite is like key active ingredient. It was what was discovered that has the ability to crack these heavy feed products. Okay, together with your matrix. Okay, because matrix is a type of alumina. You have your silica alumina combination that makes the bulk of your catalyst. Then you have your clay. The clay's job is to give it density and some form of strength, because remember, this catalyst will keep moving for the rest of his life until it's so bad that we have to change it. So the clay gives it that strength to withstand the movements, okay, over a long period of time. Then you have your binders. Your binders' job is to, as the name implies, to bring everything together. This is the binder here. Okay, let me bring my marker. This is the binder here. Okay, you can see it's like a sellotape. You know, it's sticking everything together. Okay, and you can now have additives. Additives are things that help to advance or promote certain characteristics that the client or the operator wants. Okay, so this is how catalyst looks like in the bottle. Okay, this is a sample when I was in one of my assignments. This is a sample of an e-cat. Now there are two types of catalyst. There's fresh catalyst and there's e-catalyst. E-catalyst is catalyst that's already been used, okay, for the process. And fresh catalyst is catalyst that has not been used. It's usually sent into the reactor to make up the losses, you know, or to increase activity in the system. Now, there are different types of additives. There is a ZSM5, which is used in producing increasing your olefinic products like propylene, you know, butylenes and the rest. You know, ZSM5 reduces the yield. Okay, it's kind of like enhances the yield of unsaturated LPGs. So if you look at this, the more ZSM5 you add to your catalyst, the higher your propylene and the higher your butylene, your mixed butylene. Remember that FCC is usually, if a refinery is going to have a petrochemical complex beside it, FCC is critical because propylene is probably one of the most expensive products from a refinery. In fact, if you have propylene, you know that the refinery is making a lot of money. Then you have your CO2 combustor promoters. Sometimes you may have issues with incomplete combustion in your regenerator. And that's very bad because if you have CO being produced out of CO2, the CO is a partial product. It still has to get oxidized to CO2. And that oxidation takes a lot of energy and produce a lot of heat that can make your regenerator to go as much as 800, 900 degrees, which is not good for the metal. It can weaken the metals, can weaken the cyclones. Then for environmental issues, you don't want to have, you want additives that can reduce your SOx and NOx emissions. You know, they'll reduce them, make CO2 to come back to H2S. Okay. They have metal passivation additives to prevent the effect of metals like vanadium and nickel. Then you have bottom conversion to increase conversion at the bottom, the LCOs and the rest. Okay, so at this point, I want to apologize for the video because the video would have made this particular slide clearer. But with all we have talked about, any questions? I want questions, please. I want questions from you guys. Any questions? Okay, Ali, free to go.
Okay.
Is Ali the only? Is Ali the only person? Ali, you can keep asking your question, but is Ali the only person in this forum? I want more questions. Ali.
I think some of them having a problem with the English. I think.
Oh, okay,
Yeah,
okay,
yeah.
Okay. Sorry about that.
Okay, so sir, please, I have a question about the reactor phase. When the feed is entering, you said it's oil or crude oil, but I heard from previous lectures, it's mostly will be VGO. Is that correct, or this is an operational thing?
No, the feed. Okay, so let me take you back to one of the old slides. Sorry. These are the potential sources of FCC. Okay, so now let me, I told you VGO, which comes from the vacuum distillation unit, atmospheric residue, okay, DAO. Now let me, in this block flow diagram, okay, here are the potential sources of FCC. This AR can be fed into this, depending on the FCC's configuration. This is your vacuum distillation, okay? You can have your vacuum gas oil this is your vacuum gas oil, fed into this FCC, okay? You can have hydrotreated or desulfurized AR or vacuum residue fed into this FCC. The FCC can take a whole lot of heavy hydrocarbons, a whole lot. Some are not even here, okay? But what it was initially designed for, in the good old days, was vacuum gas oil, which is this guy here, a product of vacuum distillation. But because over the years, people are trying to push the limits of this process, it's gradually being designed for so many other things. Does that answer your question? Ali?
Yeah, with you, sir, it's clear. But I have another question, if you may.
Good. Yeah, you're free.
When the top products leaves from the RX and goes for the MC, the main column, you said it's gonna be a vapor or gas phase for the gasoline.
Yes.
Okay,
Hot,
and then it's hot. So when it leaves the column, the main column, it's gonna be also like a gas or liquid phase. And how can, if it leaves as gas, how it can be converted into liquid?
Okay, so you mean when the reactor vapor comes into this main column, how does it get converted to liquid?
Exactly.
Okay, that's a very, very nice question. Okay, so you believe, do you agree with me that there are three states of matter? I mean, there's fourth state anyway, but for your level, I'll consider on three. There are three states of matter. There's liquid, there's solid, and there's gas. Correct?
Yeah.
Okay, so water can be solid, water can be gas, water can be liquid. Correct?
Absolutely.
All right. So when water is vapor, if you cool water down, it turns to liquid, correct? Imagine you're boiling water for tea, okay, and you see your vapors coming up. You can cool it down to bring it back to liquid state, right?
Yeah, exactly. It will condensate.
Exactly. So just imagine it happening here. You have your reactor vapors at roughly 560 degrees, 530 to 560 degrees, okay? Very hot. Now, the state of the vapor, the vapor has everything inside. It has your slurry oil, it has your HCO, it has your LCO. LCO is like diesel. It has your gasoline, which is in your car. It has everything packed inside. But what we then do is the distillation column is designed, okay, based on temperature gradients. Okay, the first thing we do is, if we allow the vapor to come in here, it will just rush up here and go through here. But I told you that there are different pump arounds. And what is a pump around's job? A pump around's job is to take out heat from a particular section of the distillation column. So first of all, the reactor comes in here. We use very dense, thick slurry oil to flush the vapors. Now, when we flush the vapors, the slurry oil will take out some of the heavies out of the vapor. It's a very, very rapid the superheating process. Okay, it takes it down. The vapor still keeps climbing up. Then the HCO will pump and have contact with the rising vapor. From there, the vapor starts condensing. Some vapor will still want to go up, and the LCO will pump around and come in contact with the vapors and take out, make some of the vapors to turn to liquid, depending on the level of the column. So will the naphtha, so will the reflux. Okay, so this, and while it does this, it's taking out the heat. You can see different heat exchangers. It's taking out the heat from this system because it's super hot. It's very hot. Okay, so it's taking out the heat, and as it takes out the heat, liquid products will start forming on the various trays of the column. Do you understand?
Yeah, it's totally clear, sir.
Okay.
Thank you very much.
Yeah, so it's the same with your distillation process, your CDU, crude distillation process, but the only thing is that the feed comes in here, and it's a two-phase feed. Okay, so that's basically what happens here.
Okay, thank you very much, sir.
All right. Any other question before we move to the products?
I have a question, sir.
All right, shoot.
So, I'm working at my university of a project, production of enhanced gasoline.
Sorry?
So,
prediction of what?
A production of enhanced gasoline, improve the gasoline.
Okay, from which unit? FCC or, gasoline
Yes,
can go
the
from different
FCC unit here. One of the ways to improve the gasoline, it is the FCC unit. So we had a problem of knowing the type of the catalytic that used in this unit.
Okay. So just as I explained in the last slide, let me open that up. Sorry, I'm coming. Here's mine. Okay. Just as I explained in the last slide, okay, the catalyst of the FCC is not manufactured by the person that designed the FCC. There are different catalyst vendors, your BASF, your Kerogen, these are different companies that produce FCC catalysts. Your Grace is the company that produces. These are the three major companies that produce FCC catalysts. These catalysts are produced based on the specification of the customer. The customer may want, most customers want improved gasoline yields. But from my experience, I don't really think catalyst choice really affects that. Most of the catalysts, they practically behave the same. The things that make the difference are how the FCC is run over time, okay? The operating conditions, like what is the optimal reaction temperature? What additives are you adding to prevent issues in the FCC? The likes of Grace, BASF, and Kerogen, they produce virtually the same kind of catalyst, in my own opinion, okay? But there might be some slight differences. Some catalysts may have more cracking abilities. Some may have the ability to deal with impurities more. It depends on what the customer wants. Because saying you want gasoline yield is a very, very big question. we have to come down to, okay, do you want more LPG? Do you want more olefinic gasoline? Do you want more volumes? Do you want more yields? There are specific questions that we need to ask. So what I would say is, the catalyst is good, but I think, in my own personal opinion, I think the way you operate it generally, is what makes the difference. Okay. For catalyst type, I'll recommend you check for, as I said, BASF and Grace. These are major two catalysts that produce the best catalysts in the market. So if you're looking for yield, yes, you can go for these two. Okay.
Okay, I got it. Thank you. It's clear now.
Yes. Okay.
Sir,
Any other questions?
please.
Is there any more questions? Okay.
Sir, please. Before you proceed, I have many questions to ask. In the
Yeah, shoot,
previous
shoot.
slide, you mentioned that the feed is atomized before entering the FCC unit. What is the
Yes.
atomizing size for the droplets?
That's
That's
a very
suitable
good
for.
question.
Also,
Yeah,
I
that's a very
have
good
another
question.
question. You
Okay.
said that the separation of the catalyst at the top of the RX is 99.9% of the catalyst separation.
Yeah, if the cyclone is okay, so
Working properly.
that if it's working properly, so the efficiency, if the efficiency of the if you're operating it right, if the right velocity is passing through the cyclones, if the right type of catalyst is being used, yes, then you should have such an efficiency.
Also, that means that you have a catalyst lost with the vapor product, right?
Yes, you have
Oh,
catalyst loss in the region
okay.
and in the catalyst. Okay, yeah, I don't think I made mention of that. Yes, so you have catalyst loss. You can see this diagram, this fluidization diagram. Yeah,
Okay.
this tiny catalyst. Some of them will find their way here and leave. Some of them also find their way here and leave. That is why for the regenerator.
Okay, at the product, does it cause any problem or issues to the downstream equipments or damage the final product?
That's a very good question. So
Thank you.
when it
You
comes
answered.
here, yes, yeah, okay. Is that your question? Whether it has any effect here in the product? That's your question, right?
Yeah, right. Or the
Okay.
equipments.
Beautiful question. I like that. I want more questions like this. So when the reactor vapor comes in here, you will have some catalyst losses. Now, we use a lot of slurry oil as a recycle. Part of its job is to wash down the catalyst. Okay? The catalyst is usually washed down here. So in this slurry here, it will have a mix of catalyst and oil in it. Okay? Now, there is another unit. If the refiner wants to recover this catalyst, some refiners, like if you go to MRC, Kabbalah, they have a unit called filtration unit. Now, the catalyst that is in this slurry oil will be recovered in this unit. It's like a normal sieve. Okay, the oil will pass through where it will hold back the catalyst. And in some cases, you can regenerate the catalyst and put it back inside. Now, in some cases, if you don't have enough liquid in the trays, you have some trays here, you have some trays here, you have some trays here, depending on the product. If you don't have enough liquid, those catalysts can find their way up here. They can find their way up here. So that is why I say that operation of FCC is very, very delicate. If you don't develop a level of liquid in the trays, some stubborn catalysts can find their way up here and damage your compressor. I have seen that happen before. In fact, sometimes you open your main column and you see catalysts way up here, and you'll be asking yourself, how did he get there? Okay, so the unit has to keep circulating to trap the catalyst, send it down. Okay, but the bulk of the catalyst in the main column stays here. Okay.
Okay, sir.
That's a good question. That's a very good question.
Okay, also the size of the atomizing. please?
Yes. So I would handle that in a later slide, because in a later slide I would show you that.
Okay, okay,
Okay.
no problem. Thank you so much.
Yes, it's part of my understanding. Okay, one more question before I move. If not, we will move ahead.
Yeah, like the discussion just generated a question in my mind, sir, please. So
Who's
when
talking? Is it still Ali? Okay.
yeah,
All right.
okay,
Shoot.
sir, when you just said like when you open like the top of the main column, you find catalyst, and you said like how did it get there? Okay, so isn't that like affecting the efficiency and the cost of the whole process? Taking consider catalyst is very like expensive and could like increase the expenses of the process. Is that catalyst is like spent catalyst, or could be regenerated and recycled and reused, or it's like to the waste?
So first of all, finding catalyst in the main column is not supposed to happen. Okay, at the top of the column, it's one in a 500 case scenario. It doesn't always happen. I just give you a rare situation. I think I've seen one before. Okay, it's not supposed to happen. Okay, so um don't put in your mind that you find catalyst in the main column. No, you only find finds at the bottom of the main column. Okay, so let's get that straight. Now your question is about catalyst loss. In FCC, catalyst loss is expected. Okay, we are expected to lose catalyst, but we have there's a range of loss, because as the catalyst reduces, we also add fresh catalyst to make up the losses. As I told you, we lose catalyst in the regenerator overhead, and we also lose catalyst in the reactor product line. Okay, it's expected. Like 1% of the catalysts. I mean, in a typical refinery, we can lose about a ton of catalyst every day. That's the weight of a car. Okay, we use a lot of catalyst in FCC, a lot. Okay, so catalyst loss is expected, but it's very, 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 very small compared to what we use in the process. There's a range. It's like 0.05 pounds per barrel, of oil loss. So it's very, very, very minute. If you have a lot of catalyst loss, that is a problem, and we will need to find out where the problem is coming from. Okay, and that is why you have, like in your reactor, you have the filtration process in the slurry to take care of the catalyst in the oil. And for the regenerator, we have, as I said before, your third stage separator, your fourth stage separator, your ESPs. You need all that to take care of the losses so that it doesn't get to the atmosphere, because it's also a pollutant. Okay? Yeah, then in terms of expense, well, compared to other catalysts in the refinery, like your reformate, your isomerates, FCC is not really expensive. If you put it per kg, I consider FCC is one of the cheapest catalysts in the refinery. Okay, I mean, you don't want to compare it with your reformates, which you have platinum inside your catalyst. Platinum is more expensive than gold. Okay, so you have platinum in your catalyst. Those ones are really expensive.
All right, we got some
Well,
water.
FCC is not as expensive as other catalysts or other units. But of course,
I
it's
love
still a
saying
cost, so you
Habibi.
can't
Okay.
just waste the catalyst. Okay, it's still a cost. So effectively managing the inventory of the catalyst, putting in fresh catalyst based on the activity, and experience, know when to put them to make sure that the yields of the gasoline and your activity is maintained. All these things that are built from experience. And yeah, and with that, the refinery will run smoothly. Okay?
Yeah, totally got that. Thank you, sir.
Okay, so all right. So let's move on. I think we'll soon be coming to the end of this. So we're talking about the products. As I told you before, There are major products that we get from the FCC. We have our dry gas. The dry gas is made out of C2 and lighter gases. Okay, and this leaves from the sponge absorber, which I explained before. And sometimes they can have some acid gases, but they are treated. But the final destination of the acid or the dry gas is in the refinery's fuel gas system. Okay, the dry gas from the FCC, is very, very good, because it has a relatively higher calorific value. It has some olefinic components in it, and when used, it will go to other burners in the refinery. Now, some of the things we need to consider in the dry gas is the level of C3 plus. We don't want C3 plus to be in our dry gas because it means we are losing valuable LPG. Okay, so we need to keep it as C2 plus and above. If you have C3 plus in your dry gas, then it's a cause for worry. It means one of the columns is not doing its job. Okay, we also have the LPG. We have LPG. So when I put LPGs, because you have saturated and unsaturated LPGs. You have your propane, propylene, butane, isobutane, and the likes. Okay, these can either be used as a direct fuel for cooking or a feedstock for petrochemicals like propylene. You can also blend C4s in your gasoline to beef up the RVP. RVP means reduced vapor pressure. It's an important component in your gasoline blending pool. And it's also a feed for your alkylation unit. Alkylation is an acid-based unit. I'm not going to talk about that for now. The LPG yields can be increased by, adding your ZSM5 catalyst additives, I told you before. And there are some operational methods you can do to increase your LPG yield, like increasing reactor temperature, increasing catalyst to oil ratio. The typical range of catalyst to oil ratio in the riser is 4:1. What I mean by 4:1 is like 4 weights, we can say 4 kg of catalyst to 1 kg of feed. And in some cases, 10 kg of catalyst to 1 kg of feed. So you need a lot of catalyst. A lot of catalyst in this process. Okay? Now, the next product is gasoline. This is the most valuable product in the FCC. You can increase it by, of course, playing with increasing catalyst oil ratio, increasing reactor temperature, to an optimum, because there is like in your engineering mathematics, there's an optimum value of temperature to give the best yield of gasoline. Okay. Now, there are some things we need to consider in the gasoline quality. First is octane. I know as chemical engineers, you must have heard about octane number. And to brush up your knowledge about octane, octane is the quantitative measure of fuel mixture's resistance to knocking. Now, what that means is there's a range of N-heptane, which is a straight chain, 7-carbon straight chain, and isooctane, highly branched chain. And N-heptane is 0, and isooctane is 100. You try as much as possible to produce gasoline that is in the 90s and 80s of your octane number, because anything below that, your engine can knock. Okay, and what does knocking mean? Knocking simply means that at high pressure, when the pistons are working, gasoline engines, when they are working at high pressure, it combusts, which is not supposed to be so. Okay, octane kind of like douses that effect from happening, so that it's more like a spark rather than pressure control, unlike your diesel engines. Then you have to control your benzene. Remember that benzene is carcinogenic. Now, benzene is not much of an issue in FCCs. You find this issue in reformates. But because we can also have benzene formation in FCC, we take note of that. Then the last is sulfur. FCC is the biggest contributor of sulfur components to the gasoline pool. Okay, and we all know what sulfur can do to the environment. So these are things that we need to check in the gasoline products. Okay, either by treating it, when it is being produced. So we have life cycle oil. Life cycle oil is the equivalent of diesel in a distillation column, but the only thing is that it is olefinic, and the measure quality of LCO, the measure metric in LCO, life cycle oil, is cetane number. Okay, but cetane number favors a straight chain diesel, meaning that the LCO, because of its olefinic nature, has a very low cetane number. Now, this can be corrected by taking the product to another unit for hydrotreating to increase the paraffinic nature of the LCO. Now we have the LCO and the decant oil. The LCO is not really taken as a product. It's usually used just as a pump around, as I've shown you in the previous slides, and to transfer heat to other parts of the unit through heat exchangers. And you have your decant oil. The decant oil, that is where you most likely see your catalyst finds. Somebody asked a very good question. And it can be sold as carbon black. At the end of the day, it's the least valuable product in the FCC. So you try to minimize the LCO, you try to minimize the HCO, you try to minimize the FCC, the main column bottoms, or your slurry oil, your decant oil. Okay. Now, if you take out all those products and divide it by the feed, that's feed minus this product, you have your conversion. So a unit that has conversions of 76 to 81, volume percent, means that it's producing a lot of gasoline and LPGs, and in some cases dry gases. And you're minimizing these products that don't really have as much value as those ones there. So as an operator or as an engineer, your job is to make sure that this conversion ratio is high for the FCC by minimizing this, which will give rise to higher gasoline and LPG products. Now, finally, we have the coke. And I wish that video can play so that I'll be able to explain some things for you. I hope our IT person is working on the is working on the video. Now we have the
yes,
coke.
we are working on it.
Okay, all right. Now we have the coke. Coke is a necessary. I don't want to say it's a necessary. Okay, it's a necessary byproduct in the reaction. So again, I said I wish we had watched that video so that you understand this coke path. But coke is necessary. It's a necessary byproduct by the FCC. Okay, more than 90% of the heat generated from burning the coke in the regenerator supplies the heat for the cracking. So without the furnace to provide that heat, okay, but the regenerator provides that heat by burning coke. Now there are different types of coke. We have catalytic coke, which is a function of cracking, the function of cracking, because it's a product too. You have contaminant coke, which is coke that comes with metals, like when you have your metal contaminants, in the feed or somewhere else. You have your feed residue coke. This usually arises from cokes with, like when you're trying to crack heavy feeds like residue, atmospheric residue. Then you have cokes that come like this. Then you have catalyst circulation coke. This is coke that is formed in the stripper. This is coke that is formed in the stripper section of the reactor. Okay, if not done properly, if not stripped properly. Okay. Hopefully if the video comes on, we'll explain this part again. Now for the last session of this presentation, before I go enter this, I would like somebody to ask a question. Okay, I'm expecting some questions. Any question? We're entering the last huddle. Any questions so far? Okay. So everybody is an FCC expert. That's good. Let's continue. All right. So while discussing with what's her name again? The first person that's reached out to me, Abran, I guess that's her name. I discussing with Abran. She said she wanted us to also talk about optimization options. You know, things that can be added to the unit to make it work a little bit better. Okay, and there's so much that can be added to an FCC. There are so many things that can be changed. Some problems might arise, and the engineer might say, "Okay, let's do this, let's do that." There's a host of things that can be done. But for the sake of students, I'm gonna just talk about a few, just only 4. Okay. Now, these are optimization options. So the first one is feed nozzle, feed injection, and nozzle. Feed injection, nozzle. Now, to the guy that asked me the question regarding atomization, please pay attention, okay? Let me use my pointer. So this is how a nozzle looks like, okay, in the FCC. Now, this is just one. Depending on the size of the FCC, you can have 4, 5, 12, 18, depending on the diameter of the riser and how large the riser is. This is the riser, and I'll come back to this, okay? So the goal is when the oil comes in, we still put in steam. The steam helps in, okay, not only raising the temperature, but helps in atomizing the crude, the feed, okay? So these are ligaments or globules, right? And droplets. So this is how the droplets are. Okay, this is how it happens. So something as thick as that will be heated up to reduce the viscosity, and steam together with the oil will be injected inside here, and it sprays. This is how it looks like. So this is how it's injected into the riser, so that the catalyst can have the maximum contact tendency with it. Now, for us to understand how this works in the riser, if this is the riser, okay, I'm not going to explain details about the computational fluid dynamics of this, but if this is the riser, these are injection points, okay? With a particular feed nozzle design, you can see that the atomization here is too poor. Now, by the time it gets to the top, you still haven't atomized everything. And as a chemical engineer, you're supposed to know that the larger the surface area, better the reaction kinetics or the reaction possibility, okay? Now, if you don't atomize well, it will go up, and it has a lot of downsides. Your conversion will be affected because you didn't increase the surface area properly. You have a lot, and if the conversion is affected, you produce more products that you don't want. You may also produce more gas, which you don't really want. You're interested in LPG and gasoline. And if you produce more gas, it will affect your wet gas compressor. And in some cases, the air blower coming to the air coming to the regenerator, because you also produce more coke because the reaction is not complete. But if you look at this one here, you can see the feed comes in and it is atomized. At this level here, the feed is 100% atomized. Okay? And reaction takes place perfectly. Is that clear? The guy that asked me the question, where is he?
Yes, sir, it's clear. Thank you.
All right. So this explains everything you want, okay? And this is how
Yeah,
nozzles look like.
crystal clear.
This is how nozzles look like, okay? All right. Now, the second optimization option is what we call a catalyst cooler. So because in the modern FCCs, we are processing very heavy, the refiners want to push the refinery to the limit. We are now processing very heavy vacuum gas oils or atmospheric residues, very heavy. And in the case of atmospheric residue, you have a very high Conradson number, which I spoke about before, Conradson carbon number. That's the coke forming tendency of the that's the coke forming tendency of the unit. Okay, so for feeds or for feeds that have such high numbers, when it is time to burn the coke in the regenerator, you agree with me that the coke would make the regenerator to be very, very hot because you have relatively higher coke, right? And you don't want your regenerator to be so hot. You don't want the regenerator to pass like 700 degrees centigrade. You don't want it to get to 750 or 800. It's a disaster waiting to happen. So because that can happen, if you use feeds that behave like this, somebody smart came up with catalyst cooler. So this is a form of device that will be cooling the regenerator catalyst in the regenerator. Okay, so it prevents the temperature of the regenerator from coming so high, which can cause a lot of problems. And if the temperature is too high, it will also reduce the amount of catalyst coming into here because of the energy balance. So with this, you reduce the temperature and this unit works efficiently. Now, how does this work? This is an expanded version. You blow air from here, okay, and when you blow air from here, it drags in catalyst into this cat cooler. Now, this is a cooling tube. Boiler feed water is used to cool the catalyst, okay, and after cooling, it forms steam. So the fluid that leaves here is high pressure steam, which can be used in somewhere else in the refinery. And the cold catalyst comes down here, goes through here, and goes back to the unit, gradually moderating the temperature of the regenerator so that it doesn't go so high. Okay, so that is, and with this device, you have you can control the catalyst oil ratio. You can now easily control the reactor temperature because you don't want very extremely hot catalyst to come into here. It can also damage this. You can control them independently with this. Okay, I know someone's going to ask a question about this, but let me explain one more slide. Now I'm going to explain these arms. Okay. Now this is the kind of refinery. This is the kind of FCC that is in Kabbalah refinery. It's a very nice FCC. Now, in cases, I spoke about when you have high Conradson carbon index number. You're trying to take out the heat from the regenerator. Now, in this case, when you talk about the RexCat FCC, this arm, in a case where the coke forming tendency is very low, the disadvantage of having that kind of scenario is the regenerator will not have coke to burn. You have a minimum amount of coke that is being formed on the catalyst. And if the coke on the catalyst is small, then there's no heat. So the FCC will just die a gradual death because it will getting colder and colder and colder because the coke cannot form on the catalyst. So someone came up with an idea and said, okay, since the bulk of the coke is formed here before going to the regenerator, why don't we just keep, recycling the coke inside here with the catalyst, with recycling the carbon, the catalyst and coke inside here, and recycling the fresh catalyst inside here, and maintain the coke levels in the regenerator. With that way, the regenerator will not go down in temperature because there will always be coke forming in the unit. I know this is kind of complex, and I appreciate the complexity, but I know that one day you will get it. But for those who have questions after this, please go ahead and ask me after this presentation. Now, the last arm is the recirculation arm. This arm is for a special type of FCC. This job is to assist with continuously burning the coke. If there's imperfect coke distribution in the regenerator, it will take it back to the combustor and burn it. Okay, these are things that the operators can control. Okay, so as I said, it's used to enhance coke born in the combustor type reactor, and this is the combustor type reactor because this is where the combustion goes on. Now I know this is pretty complex, and I appreciate, and I know that for those who will study more, they will get the hang of this. Now the last optimization option I'm going to present is oxygen enrichment. Now I told you that hot air comes in to assist in burning the coke on the catalyst. Okay. Now, air is a mixture of gases, and oxygen, which is the primary component of air for combustion, is 21%. So what that tells you is for every 1 kg of air, or for every 1 metric cube of air you put in, only 21% of that 1 metric cube is going in for combustion. The remaining is just occupying space and maybe fluidizing, quote unquote. Okay. Now, what people have decided to do is, if they are struggling with 100% combustion, that is converting coke to CO2, some refiners are now adding extra oxygen into the air to move it from maybe 21% volume to maybe 23 or 24. Okay, it's needed for combustion, which is oxygen. And by doing that, you are not you're not going to strain the generator. Rather, you are increasing the efficiency of the combustion. Okay, so that's a very smart move that refiners do. Once in a while, maybe when they're struggling with controlling the temperature or runaway temperature or inefficient coke burn in the generator. Okay, and with that, I think we have come to the end of this presentation. In summary, we have achieved the following. We have presented a comprehensive introduction to FCC basic concepts, operations, and issue in the refinery. We have also introduced major equipment and their functions in the FCC unit. And we have presented some optimization options available in FCC and how they improve efficiency. Okay, so these are my references. Thank you very much. Okay, so I've come to the close of my presentation. So at this point, I want questions from everybody. Okay? Thank you.
Sir, I think we found a solution for the video. Do you
Okay,
want to
please.
present it? Can you please turn off your screen share and open your video from the browser and share the video from the video tab?
Oh, wait, say that again. Say that again.
Okay, so turn off your screen share.
Okay, like this.
And from your browser, open YouTube and open the video.
Oh, okay, makes sense. All right. I get that. Okay.
Okay, and share it from video tab.
Okay. Let me get the link. Yeah, just give me a sec.
Okay, take your time.
Okay. Yeah, so let me get the link. Okay. Okay, so let me share. Okay. Okay. Share. So I'm gonna share the web page, correct?
Yeah, from video tab.
Okay.
This video summarizes the process and the function of each component.
Yeah, it's working now. Great
Okay.
job, sir.
All right. You see, you guys are young. I'm old. Okay. That's good. That's good. Kudos to the
Yeah,
IT
there is a
person.
solution for every problem.
Yes, there's always a solution. Okay, so I want to make this.
An important part of the refining process takes place in the facility's Fluid Catalytic Cracker, or FCC unit. In the FCC unit, heavy hydrocarbons from crude oil are broken or cracked into smaller hydrocarbons, which can then be processed in gasoline and other fuel products. The heavy hydrocarbons are first fed into a reactor, where they mix with the catalyst. The heavy liquid hydrocarbons are converted into lighter hydrocarbon vapors as they travel up the reactor. At the top of the reactor, the lighter hydrocarbon vapors are separated from the catalyst. The hydrocarbon vapors then flow to the main distillation column.
So the question of somebody asked a question about vapor. I think that was Ali. So the vapors go to the bottom and is superheated.
The catalyst falls down the side of the
Oh, sorry. Okay.
vapors then flow to the main distillation column. Catalyst.
Now, these are cyclones, okay? Somebody asked about the percentage efficiency of the catalyst. Let's just say 99.5 to 99.9. I mean, depends on how you operate it. So you can see the fines falling down. When they spin, they will drop.
Falls down the side of the reactor where it moves.
And this is the stripper section where they weigh.
Through a slide.
In this section, we can put steam, and steam will be bubbling through here, removing any hydrocarbon that may be attached. Okay, but the coke is still intact. Okay.
Valve to a piece of equipment called the regenerator.
Now this is the regenerator. Now I didn't speak about this. These slide valves are very important. In fact, these slide valves are the reason why this is not a bomb. Okay, because here is the fuel side and here is the air side. Imagine if the fuel comes into here. You're gonna have an explosion, right? So the job of this slide valve is to make sure that this doesn't come in here, and the barrier between here and here is the catalyst. Okay?
During the reaction.
Now this is the catalyst. You can see it's covered with coke because it has done its job. It has performed this, its cracking activity, and coke has been deposited as part of a byproduct, as I did mention before. Then the regenerator burns.
A layer of carbon called coke forms on the catalyst that must be removed. Inside the regenerator, air is.
Now, if you don't remove the coke, it gradually reduces the activity of the catalyst. Okay, that's why we need to remove it.
And the coke on the catalyst is burned off. The catalyst is then fed back to the reactor through a slide valve, and this.
Now the burnt catalyst or the regenerated catalyst is now fed through the slide valve. This is the regenerated slide valve into the feed.
When the coke is burned off the catalyst.
Please, are you guys also hearing my explanation as the video is going?
Yeah, we are hearing this.
Okay, beautiful. So, as I said, product of combustion, flue gas, CO2, that is what is all this. Okay. The catalyst fines will be moving around with this, but they will have to enter here, spin, and come down. But some stubborn fines or stubborn catalysts will follow it up.
Off the catalyst. This creates products of combustion called flue gas. The flue gas flows out the regenerator and enters a system comprised of multiple pieces of equipment, which remove any remaining catalyst particles present. The regenerator and flue gas system comprise the air side of the FCC unit. The last piece of equipment in the flue gas system is called the electrostatic precipitator, or ESP. The ESP removes small catalyst particles using static electricity. While the ESP is energized, it creates sparks, which are sources of ignition.
Okay. Alright. So, okay, YouTube and the advertisement. Okay, so where are we? Okay, so that's majorly the animation, which explains everything. Okay, so let me. Okay, so at this point, I'm done with the presentation. Before I ask for questions, so how was the presentation? Was it easy to understand? I think it was complex. Was it straightforward? I know there are a lot of uncertainties, which is normal. I mean, I would have done the same. So what do you guys think? Okay, I'm saying it was fantastic. Okay, Ali? Yeah, you've been paying attention. Any other comments before we ask the last questions?
No, the presentation is great.
Oh, okay. Thank you very much, Treasure141. That's an interesting name. Okay. Questions. I guess what's the time in Basra right now?
It's now 10 p.m.
Wow. Oh, okay. All right. So, any questions? So we can call it a night, a day. Okay. I think everybody's an expert right now, so that's good. Oh, okay. Thank you very much, Ali. Thank you very much. So,
Thank you, Professor, for your valuable information. It was a wonderful lecture in actual.
okay, no problem.
Thank you very much. Thank you to all the attendants. I hope the lecture will come to the registration before leaving the lecture, and have a good night. Goodbye. If you have any question, let the sir hear it.
I think everybody's an expert, so which is good. Okay.
Thank you very much, sir.
Okay. All right. Thank you very much, and all the best, and have a wonderful day or wonderful night. Okay. Yeah. Bye.
Good night, sir.